All right, hey you guys, let's jump right into our Unit 2 review for the AP exam. This is all about bonding. Please excuse whatever noises you hear in the background. I bought this fancy mic, so hopefully my audio sounds better, but of course my husband is in the kitchen cooking dinner. So if you hear any banging around or fire alarms going off, that's why. Anywho, ionic, metallic, and covalent bonding. Here we go. We're going to kind of fly through this. Remember that ionic bonding is the formation of a compound between a cation and an anion. So we're talking about this transfer of electrons. Whoa, that came out really dark. Between a cation and an anion. These are typically between metal to non-metal atoms. Of course, though, these can also include our polyatomic ions as well. And of course, in order to become a cation and an anion, there has to be a transfer of electrons from the cation to the anion, cations being positive, anions being negative. I feel like my handwriting on this thing is getting worse and it's making me absolutely bonkers. Oh, I'll be okay. Okay, so what is the force of attraction that holds together a positive charge and a negative charge? That's right, everybody. Maybe if I just write really slow. Electrostatic potential energy. Constant. Charge number 1. Charge number 2. Divided by those distances between those charges. So remember, when you have small radii, really small distance between those charges, you're going to have bigger electrostatic potential energy. You're also, when you have bigger magnitude of charges, when you have ions with like a 2 plus or a 3 plus charge, you're going to have a bigger numerator and thus a bigger electrostatic potential energy as well. And this is, of course, how we measure the strength of this crystal lattice structure, and it's called lattice energy. Remember with your crystal lattice structures that your cations are smaller. So like these blue ions here in this diagram, those blue ions are my cations, and the green ions are my anions. Okay, what else do we want to talk about ionic bonding? Oh, I know. Let's draw a quick little Lewis dot structure. So for example, if we were forming magnesium chloride, magnesium with its 2 valence electrons, chlorine with its 7, we can show the formation of an ionic compound with a Lewis dot structure similar to how we would do for covalent, but we're showing a transfer, not a sharing of electrons in this case. So magnesium can donate 1 electron there to satisfy chlorine's octet, but we would need a second chlorine atom in order to accept that second valence electron from magnesium. And so we would end up with a magnesium cation with a 2 plus charge and 2 chloride ions, each with a 1 minus charge, and thus a final formula of MgCl2. And of course, when we go to name ionic compounds, we don't use prefixes because those charges have to balance. This is the only formation of magnesium chloride is MgCl2. Oh, properties. I almost forgot to talk about properties, you guys. Because of this crystal lattice structure, this is a very strong structure, very rigid structure. So because of this crystal lattice structure, maybe I should write down crystal lattice underneath it in my new terrible handwriting. Maybe I'm getting carpal tunnel from this thing. This crystal lattice structure results in these being solid at room temperature most of the time. There are such things as ionic liquids, but they're very, very unique. So these are solids with high melting and boiling points because of that strong lattice energy. And they are very brittle because if you were to smash this with a hammer or apply a force to it, those positive charges will repel one another, which will result in that repulsion will result in a shattering of that structure. I'm doing hand and arm signals as if you guys can see me. Anywho, what else? Oh, maybe I should remember to show this to you guys if you guys come to extra help tomorrow. These are also conductive when aqueous because those charged particles floating around in solution allow a current to pass through. So these are conductive only when aqueous or melted into a liquid. They would also be conductive. Okay, great. Done with ionic. That wasn't too painful. Let's talk about metallic bonding, shall we? Does anybody remember the name of this structure? Let's switch to green. This structure is called the sea of electrons. Characterized by, as you can see here in blue, these are called, oh my God, my kids are running around like a herd of elephants. I'm so sorry. Why did I even bother buying a good mic? These are called delocalized. Oh my God, they're wrestling now. These are delocalized electrons. These electrons are free to move around this structure. And I think the word bonding here is a little bit of a misnomer. I think oftentimes, you think about bonding, you think of atoms of different elements being held together by a transfer or sharing of electrons. You can have what we call metallic bonding even if you have just a pure metal. So let's say this was just a pure sample of zinc. What we're talking about is the force that holds together this sample. So you would have a zinc with a 2+ and a zinc with a 2+ and a zinc with a 2+, etc., all throughout this structure. But what's interesting about metals is because they don't really care about their electrons, those electrons are just free flowing all throughout this structure, while you can see these metal cations remain very sort of orderly and in place because those positives are repelling one another. So this force of attraction between the positives and the delocalized free-floating electrons is sort of the intermolecular force, if you will, that holds this structure together. Okay, so what kinds of properties do we have based on this structure? Well, certainly metals tend to be solids, again, like ionic compounds, the only one being mercury, that is a liquid at room temperature. And these are conductive even in the solid state. So they don't have to be aqueous in order to be conductive because these free-flowing electrons can carry charge right through this structure. Metals are malleable, meaning they can bend. They're also called ductile. They can be drawn out into wires because these free-flowing electrons can prevent cation repulsion. So if you were to smash this with a hammer, these electrons could just swim in between those positive charges and prevent repulsion and shattering like we would see in a brittle ionic structure. Did I write brittle up there? I feel like I didn't. Oh yeah, I did. Okay, good. Okay, so they're conductive, they are malleable, and they're also shiny. And the chemistry word for that is lustrous. And the reason why they're shiny is because free-flowing electrons are able to reflect light. Now, there's two more vocabulary terms that the AP exam really likes. I don't really know why. We didn't talk about them when we did our bonding notes, so we'll talk about them now. And these are two different types of alloys. First of all, you should remember what an alloy is, obviously. An alloy is a mixture of metals. And the reason why we make alloys is so that we get blended properties of both of the metals that we put into the mixture. We can strengthen metals, we can make them more malleable, we can change their melting and boiling points, lots of different things we can do. There's two different types of alloys. The one you see on the left is called a substitutional alloy. A substitutional alloy is when you have atoms with similar size radii. So if we were to mix together two metals of similar size radii, we get this arrangement where it looks as if this green metal atom has taken the place of one of the black ones, a substitution, if you will. So substitutional alloys are between metals of similar radii or similar size. Okay. An interstitial alloy is if you mix together metals where one is much smaller than the other. Where one radius or atom. You know, I'm always talking about the atoms here, obviously, where one radius is much smaller. And when you have a radius that's much smaller, as you can see, those atoms can actually sort of fit inside or in between the atoms of the other metal, and thus the interstitial, the inter prefix in an interstitial alloy. So it's all about radius size. You can also, oftentimes we call metals that have been interstitially mixed with carbon atoms, even though carbon isn't a metal. That is a very common interstitial alloy where we mix carbon into the structure as well. So you can have some nonmetals mixed in with your metals as well and still consider them to be alloys. Okay, moving on to covalent bonding. Covalent bonding is obviously sort of like the opposite of ionic bonding, where you have a nonmetal bonded to a nonmetal through a sharing of electrons. Now, why do we share electrons? Same reason we transfer electrons, in order to get to a full valence shell. So if we were looking at the electron configurations, let's say for hydrogen, the 1s1, that is an 1s orbital that is half full. If I have another hydrogen atom with a 1s1, I can get to a full valence shell by sharing those two 1s electrons, because we know that a 1s2 is a full valence shell. So we're always trying to satisfy this octet rule. Well, in the case of hydrogen, a duet rule. So I want you guys to think about these things when you're thinking about bonding. Also be thinking about the quantum mechanics involved. And if we wanted to sort of visualize this, we know that a 1s orbital is a sphere. Let's see, if I go really slow, my handwriting's better, but I don't think you want to wait that long. Okay, and here's my other hydrogen. Oops, 1s. Okay, now there's one electron here in this orbital and one electron here in that orbital. But if these two orbitals were to overlap between the nuclei, we would now have attractions with this proton to this guy's electron and this guy's proton to that guy's electron. And so that's what a bond is when you have this orbital overlap between the nuclei. Remember, we call those sigma bonds. Now, there's like an ideal distance here. There's like an ideal bond length. Too far apart, there's no attraction from these protons to those electrons. And too close together, like if I overlapped these things like right on top of one another, like so. Well, I'm not gonna be able to draw two circles on top of each other. Ignore that. Just imagine if my two nuclei were very close together. If my two nuclei were very close together, I would end up with the protons repelling one another. So too close is bad. That's not going to form a stable bond. And too far apart is bad too, because then you don't even have the attractions of one proton to the other atom's electrons. You don't have any sharing of electrons at all. This one is like just right. So the bond length is going to happen at a distance where you get the protons attracting the other atom's electrons without proton-proton repulsion. And so that is where your molecule is going to be the most stable. That is what's going to determine your bond length. Now, of course, we can also see that here in this potential energy diagram. In these diagrams, it is showing you where the bond is occurring. And of course, wherever the potential energy is the lowest is your most stable position. So like this is where we have the most stability. And so this is the lowest potential energy, and where it crosses that X or that horizontal axis is your internuclear distance. So this would give us, this distance here would give us our bond length. In the case of hydrogen, a hydrogen to a hydrogen, that is a single bond. And typically, single bonds are longer And then double bonds are a little bit shorter and triple bonds are a little bit shorter. Okay, so that was our single bond. So typically it goes single bond is the longest, double bond is the shortest, is shorter, I should say. And your triple bond is your shortest. So when we go down and we increase bond order, when the bond order goes up, the bond length typically goes down. Now notice how I keep saying typically. All right, I don't like how any of that looks. It's very, 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 very ugly. Will you stick with me while I fix it? Okay, thank you. Hydrogen, this was my hydrogen single bond example. Now, let's say I was talking about a single bond, then a double bond, then a triple bond. Okay, so as we go down this list and we increase in something called bond order, which is just the amount of shared electrons, as we increase bond order, we also increase bond strength. But we tend to decrease bond length. Now, I'm going to challenge that notion here in a second when we look at this practice problem down below. Okay, I think you've probably seen this problem before. Let's take a look at this problem. Remember, on these potential energy diagram graphs, the lowest point in the graph is where you have the lowest amount of potential energy. That's your most stable position, and that's your bond enthalpy. That's how much energy you would need to input in order to break that bond. So we can clearly see on this diagram that the Y2 molecule is the strongest bond, like by far. And the next strongest, it appears, is the Z2. And the X2 being the weakest. So just based on this strongest to weakest, you would think that your Y2 would be your triple bond, that your Z2 would be your double bond. I don't know why I drew my triple bond so big. Sorry. You would think, are you guys annoyed with me? Oh, and I didn't change colors when I started talking about covalent. I stuck with this like colors I was using for metals. Ay, ay, ay. Lindsay, get rid of that Rivera Khan Academy backdrop. I'm not worthy. Okay, strongest is my triple bond. And then you would assume that the next one would be your double, and this next one would be your single. So let's just, first of all, we're talking about hydrogen, nitrogen, and oxygen. So we know that our triple bond is referring to our nitrogen. So right away, we can assume that the Y2 has to be the nitrogen because it's like so much vastly stronger. And so then our only choice for this is A, choice A. But then you want to go through and think, like, does this make sense in terms of the weakest bond? So like our single bond being our weakest bond, the X2 being the weakest, is that the hydrogen? Yes, it is. Now, what might be a little confusing to you guys is it appears that the triple bond, this nitrogen triple bond, N2, and the oxygen double bond, the O2, if this is increasing internuclear distance, it appears that your hydrogen, sorry, didn't label my hydrogen, is my shortest bond, which doesn't make sense based on what we were just talking about. When we were saying, well, single bonds are longer and triple bonds are shorter. You're like, no, look at here. This hydrogen is the shortest. And that's strange. But it's not if you actually think about what is forming the H2 bond. It's a 1s overlap. And we know that those 1s orbitals are small. Hydrogen is a very small atom. So even though hydrogen has a single bond in this case, it is quite short. It's quite shorter than the oxygen and the nitrogen double bond and triple bonds, because this is in the first period and oxygen and nitrogen are in the second period. So their radii are a lot bigger just in general. So when we say that triple bonds are short and single bonds are long, that is if you are comparing atoms of similar size radii to begin with. So if this problem tripped you guys up back in our bonding test, I bet that was probably why. So when I'm reading these graphs, I tend to look first at bond strength and then secondarily look at bond length, because it can be a little bit trickier because you have to take into account the size of the radius of the atoms that you're talking about. The hydrogens being overlapping in the 1s or the first principal energy level, and the oxygens and the nitrogens creating their bonds overlapping in the 2s and 2p in the second. This is where their valence electrons are in the second principal energy level. Okay, so I think that's all I wanted to talk about in terms of the general discussion about bonding. Let me check my notes. Yes. Okay, so now we get to move on to Lewis dot structures for covalent compounds. So just to review, we talked about the three main overarching types of bonding. We talked about ionic with our transfer of electrons and the properties that they have, and the crystal lattice structure. We talked about metallic bonding and the sea of electron structure that give metals their properties. Our two different types of alloys, mixtures of metals. And then covalent bonding, looking at it overall as a sharing of electrons, overlap of orbitals, bond order, and bond strength. Okay, so now let's draw some Lewis dot structures. I love Lewis structures, don't you? They're so much fun. Let's switch to a fun color for our Lewis structures. All right, pink purple it is. Okay, let's draw some Lewis structures. Let's recall our rules for drawing Lewis dot diagrams. Let's draw NO3, 1 minus. Rules for drawing Lewis dot structures: count up your total number of valence electrons, 5 for nitrogen, 6 times my 3 for my oxygens, plus 1 for that extra electron that we have with charge. So that's 6 times 4 is 24. Divide by 2, it's 12 pairs of electrons. I'm going to put my least electronegative atom in the middle. That would be nitrogen. Connect to an oxygen, oxygen, oxygen. Of my 12 pairs, I have 9 pairs remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm all out of pairs. I've assigned all 12 of my pairs. So now I look to see if all of my octets have been satisfied, and they have not. Nitrogen does not yet have 8 valence electrons. So I'm just going to take away one of those lone pairs and change it to a bonded pair. And now nitrogen's octet is satisfied. Because this is a polyatomic ion, I'm going to put it in brackets with a charge on the outside. Now, we look at this structure, and you might say, oh, Ms. Rivera, I drew my double bond on the left-hand side. Great, no problem. The reason why that's no problem is because no matter which way I draw this structure, no matter where I put that double bond, the formal charge is going to be equivalent in all 3 places. If you forgot how to calculate formal charge, let's give it a go. Formal charge is equal to the normal number of valence electrons that an atom has minus bonds plus lone electrons. not pairs of electrons, like total number of lone electrons. I think Mrs. Bodmer calls this minus sticks and balls. Okay, so if I'm counting up for this oxygen here on the far left, oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7, negative 1. Nitrogen has 5 minus 1, 2, 3, 4. 5 minus 4, positive 1. Oxygen is 6 minus 1, 2, 3, 4, 5, 6. 0. And this oxygen looks just like that one. Oh my gosh, my family is driving me bananas. What don't they understand about mom is recording a lecture? My formal charge, you guys. My formal charge is okay. I'm going to be okay. My children might not be. All this formal charge adds up to the charge of my polyatomic ion. None of these charges are of magnitude 2 or greater. And I don't have any negative formal charge on my central atom. You always want your negative formal charge on your terminal atoms, which are your more electronegative atoms. So this is fine. And what you might have noticed is that no matter where I put that double bond, I'm going to have that same formal charge situation, which means I have, did you already say it? Did you say it with me? That's right, resonance. And so you get to draw it all 3 times. And you're not drawing it all 3 times to satisfy your, mean, annoying chem teacher. You are drawing it all 3 times because, in fact, that double bond is delocalized. It is spread out over all 3 of those locations. How do I know that? Well, if I look at this molecule underneath a microscope, I would see 3 equivalent bond lengths. I would not see 2 long bonds. I would not see 2 long singles and a double. I would see 3 equivalent, essentially, that's not a nitrogen, that's why I can't talk and write at the same time. I would see 3 equivalent, like bond and a third bond lengths, because that double bond is delocalized. And really, you guys, that's just a fancy word for electrons are moving around. And so if they're spending equal amounts of time spread out over 3 locations, essentially those atoms are all going to be equidistant from one another. Okay, so this is how we do formal charge. This is how we draw resonance. And what else do I need to talk about? Oh, suboctets and expanded octets. There are times when we have substances, for example, like BF3, where the octets are not satisfied. So if we were to go ahead and draw, and I'll save you all of the counting, but if we were to draw BF3, we would get to this point here, where all of the fluorines had lone pairs. And all of a sudden, we were out of lone pairs. And you might be tempted at this point to make a double bond. However, if you do make a double bond in this case, you're going to make the formal charge kind of icky. If we do the formal charge right now, boron has 3 valence electrons minus those 3 bonds, 0. And fluorine has 7 electrons minus those 6 electrons plus the bond. And so these guys are all 7 minus 7. So these guys are all 0. The less formal charge, the better. Had we double bonded one of these fluorines, like so, maybe my handwriting is better when the screen is black. Do you think that has anything to do with it? Probably not. Okay. So if we were to calculate formal charge now, boron would be 3 minus 4. That's a minus 1. And this fluorine, which is 7, would be 7 minus 1, 2, 3, 4, 5, 6, a plus 1. Now those 1s, the magnitude of 1 isn't so bad, But the negative formal charge is not on the more electronegative atom. Fluorine is the most electronegative atom on the periodic table, and so like that -1 should be on fluorine if we had to have formal charge at all. So like, yeah, that's not our structure. This is. And this is what we call a sub-octet. We can also have expanded octets. Sometimes we expand octets with lone pairs. Sometimes we expand octets with double bonds. Let's do just a real quick SF6. Yes, that is a sulfur with 6 fluorines bonded to it. Have we expanded the octet of the central atom? Yes, we have. I am not going to draw in all of those lone pair electrons on the fluorines. This is an expanded octet, and this is okay. Check your formal charge on your sulfur. 6 valence electrons minus your 6 bonds. That would give you a formal charge on your sulfur of 0. And if we bothered to draw in all of our electrons on the fluorines, you would find that they are all 0 as well. So it is possible to also have expanded octets as long as the central atom is in the third period or beyond. Has to be in the third period or more. And that's because once you get into the third period, you have d orbitals available to put extra electrons in. So you can, in fact, expand the bonding octets beyond 8. Okay, so be able to draw Lewis structures. And the reason why we want to draw Lewis structures is because not only do we want to be able to predict bond length and bond strength, we also want to predict molecular geometry. And by predicting molecular geometry, we can then predict properties. So let's talk VSEPR and hybridization. VSEPR theory stands for valence shell electron pair repulsion. And that's just a fancy acronym for electrons want to be as far away from each other as possible. So electrons, both bonded and non-bonded, will arrange themselves in a geometry that minimizes repulsions. In other words, they want to be as far away from each other as possible. Remember in class when I blew up all those balloons and tied them all together and you saw those balloons arranging themselves into shapes that pushed the balloons as far away from each other as they could? That's what's happening. Now, I'm obviously not going to talk through this entire thing again, and I'm certainly not going to, again, talk through hybridization. And I would like you guys to maybe go take a look at your notes and see if you remember how we hybridized orbitals in order to explain molecular geometries. But for the AP exam, you actually don't need to be able to explain the quantum mechanics that way. I would expect you guys to know your bond angles and know your geometric names, although because this is open book, you guys could very quickly look that up. We'll talk again about what pages maybe you should tab in your textbook. And as far as the hybridization goes, you just need to know that when something is linear, it's always going to be sp hybridized. When something is in the trigonal planar family, it's always going to be sp2 hybridized. Maybe we should pull this chart up so we can see it all at once. Okay, so here we have all of our different potential geometries. And you guys were very familiar with me talking about these in terms of domains. So I'll go ahead and label these as domains. So when I talk about domains, I'm talking about areas around the central atom where bonds or lone pairs could exist. So in this linear geometry, we're talking about 2 domains. And the only way to have 2 domains is to have 2 bonded domains. So you don't see anything here with lone pair substitutions because both of our domains will always be bonded. In order to get this linear geometry, in order to explain that with quantum mechanics, we have to have sp hybridization. That gives us 2 identical sp lobes for those bonds to occur in. Okay, when we get to 3 domains, we are talking trigonal planar. They're going to arrange themselves in a flat plane, all of the atoms 120 degrees apart. Now, trigonal planar is the name of the domain family, and that would be the name if you had 3 bonded domains. Trigonal planar will always be sp2 hybridized. 3 equivalent 120 degree bond angles. However, if one of those domains was not bonded, it's still sp2 hybridized. But if one of those is, instead of a bonded domain, is a lone pair, like so, that lone pair repels more strongly than a bonded pair. And this bond angle is going to be less than 120 degrees. So the bent 3-domain molecule has a less than 120 degree angle versus the trigonal planar 3-domain molecule, which will have exactly a 120 degree angle. Stick a 4th domain in there. Now we're in the tetrahedral family. Tetrahedral molecules are always sp3 hybridized, 4 equivalent domains. If all of them are bonded, that molecule is tetrahedral. If one of them is a lone pair, it's trigonal pyramidal. And if 2 of them are lone pairs, then it's bent. And both of those 2 are going to have less than 109.5 degree bond angles. Getting into 5 domains. This is where we end up, remember, with our axial domain and our equatorial plane. So up here, top and bottom, that's our axial plane. And around the center, like the equator, is our equatorial plane. Sometimes you'll see this written as DSP3. I tend to write it as SP3D, which is, I believe, how your textbook writes it as well. SP3D hybridization creates for us 5 equivalent bonding domains. If they're all bonded, it's trigonal bipyramidal. If one of them's a lone pair, it's called a seesaw. They call it a sawhorse. If it has 2 lone pair substitutions, it's T-shaped. And 3 lone pair substitutions, and you have linear. And you can see that these lone pair substitutions are happening on the equatorial plane, where you have the fewest number of small angle repulsions. If it was an axial replacement, if you put the lone pair on the axial plane, you'd have some repulsions between the axial and the equatorial, which would be like 90 degree. You would have more 90 degree repulsions than if you just put it on the equatorial domain. You don't need to know that. I don't even know why I started talking about it. Okay, octahedral, 6 domains. sp3d2 hybridization, giving us 6 equivalent bonding domains around the central atom, octahedral being the head of the family. Start substituting in, and this wouldn't matter if you were substituting in axial versus equatorial because everything's 90 degrees everywhere. So it doesn't matter where the substitution takes place. When there's 1 lone pair, it's square pyramidal. 2 lone pairs, and it'll push it back planar, square planar. 3 lone pairs, T-shaped. And 4 lone pairs, linear. Okay. I think that's it. Oh, no. It's not. Oh, I stopped circling these things. There we go. Okay. So go back and take a look at your notes if you want to remind yourself about that hybridization stuff. But really all you guys need to know is linear is SP, trig planar SP2, and hey, that seems like something that you'd be able to look up if you needed it. Okay. Oh, I had my whole multiple bond conversation somewhere else, didn't I? Didn't I talk about like single bonds being long and double bonds being short and triple bonds being the shortest? I did. I talked about it in terms of strength. Oh, I know what I wanted to talk about. I wanted to talk about it in terms of sigma versus pi bonds. Remember, this has to do with hybridization. So go back and look at those notes. But again, it's kind of dumb. The only thing you have to be able to do is say that a single bond is always going to be a sigma bond. A double bond is a sigma bond and a pi bond. And a triple bond is a sigma and 2. Man, my Greek letters are really bad on here. A sigma and 2 pi bonds. Remind yourself that sigma bonds are between the internuclear axes. This is when we have an overlap, like a 1s overlapping with a 1s. See how that orbital overlap happens between the nuclei, like so. So when you have this overlap between the nuclei, that's what we're talking about when we're talking about a sigma bond. And when you're talking about a pi bond, you're talking about orbital overlap above and below the internuclear axis. This would be like, if you remember in our hybridization, if we had 2 unhybridized p orbitals that were overlapping to create a double bond, this overlap up here and down here, see how it's above and below the internuclear axis? This quantifies as 1 pi bond. And in a triple bond, you would have other unhybridized p's. Maybe I have to do a different color and I can't make 3-dimensional, but this would be like if these p orbitals were coming out this way, front to back, and the orbital overlap was happening here and there. That would be the second pi bond in a triple bond. Okay. And lastly, I think I'll stick with this purple color pen here. I want to talk about covalent network solids. Now, in our next and our final for this week review, when we talk Unit 3, we're going to talk about intermolecular forces, like the forces that hold, one water molecule. When we're talking about covalent compounds, what's the force that holds one water molecule next to another water molecule? You guys all remember that force is called a hydrogen bond. So those things are called IMFs, or intermolecular forces, the forces that hold together one molecule towards another molecule. Now, we didn't talk about that with ionic compounds because it's the crystal lattice structure that holds the whole thing together. And in metallic structures, it's the sea of electrons that holds the whole thing together. And in most covalent compounds, it's intermolecular forces that hold the whole thing together. However, there are some substances that what holds the whole thing together is in fact a covalent bond. Okay, so these are solids whose entire structure is held together by covalent bonds. So like it's not an IMF, it's not an intermolecular force, it's like an actual bond or orbital overlap that's holding one molecule to another molecule. And covalent network solids tend to be very strong because of that. So here are a couple of examples of covalent network solids. Carbon, this is the allotrope diamond. So this is pure carbon and this is pure carbon, but they are different allotropes. They have different sort of structures and arrangements. In space, you can see carbon is in sheets versus diamond, which is in like these diamond formations here. This obviously is like transparent and very, very hard and colorless, and the graphite being, much softer, and it sloughs off in layers when we write with our pencils because of this layered arrangement of these carbon rings. But even still, with these different allotropes, you'll notice that what's holding one of these carbon structures to another are actual carbon-to-carbon bonds, right? What's holding together this carbon ring is a carbon-to-carbon bond. Okay, so that's what we're talking about when we talk about covalent network solids. Same thing here with the silicon carbide and the silicon dioxide. We're not talking about an IMF, we're talking about an actual bond that's holding the structure together. And again, different solids can have totally different properties, even if they're composed of the same substance, because if we arrange them differently, we get completely different properties. Carbon being, graphite being a softer black substance that we write with in our pencils, and diamond being a totally transparent and hard gem. Okay, so that's actually a really good place to leave off, because we're going to go from this conversation about properties holding together these covalent network solids to discussing the different intermolecular forces that can be experienced by different covalent molecules, depending on whether or not they are polar or nonpolar. But we will save that conversation for the end of the week. Bye-bye.